So without further ado, I think we will begin with our oddball visitor from outer space. This is outer space. And so what kind of visitor came through? Well, if you've seen the news, you have already seen a video that looks something like this. This very strange object has come through our solar system. We will be hearing from our speaker in a few minutes about what that might be and why we think it looks that way. But, you know, it may look that way, or at least that's what we think, but there's no reason it couldn't also look something like that. Or perhaps something like that. I kind of like this one. There we go. And, of course, its cousin. We also have the Silver Surfer, and because we're an equal opportunity show, we have a little cleaned up version of the female Silver Surfer, if you know that one. And then all of those are jokes, of course, but the real one is this one. If you don't know Star Trek 4, that's from Star Trek 4. And that is also about an oddball visitor from another solar system. But, of course, we had to include this because whenever we have the opportunity to include Leonard Nimoy in the theater after which he is named and to honor and thank him again for his great generosity, we like to do that. So without further ado, let's welcome our not-so-oddball visitor from UCLA, Dr. David Jewitt.
So, first of all, should we deal with the name? Why not? So, it has many names. So, when it was discovered, it was referred to as C 2017 U1, because the belief was, because of its orbit, it must be a comet. And comets have a C in front, so C/217 U1. Then it was decided, no, it doesn't really look like a comet, it's an asteroid. So the C became an A. And so it's A/2017 U1. And that's a bit peculiar because most asteroids don't have an A in front of them, they just have the number. And then it was decided, well, you know, it's not really an asteroid either. It's some different kind of a thing. And so this organization, known as the International Astronomical Union, in all its glory, decided that it needs a new letter, and they unfortunately picked I, which is the most stupid pick you can think of, because on most computer screens, you know, I is indistinguishable from 1, which is indistinguishable from L. So when you read the name, you don't really know what the name is. And then, to make matters really about as bad as possible, certain people who shall remain nameless gave it a name that begins with an apostrophe, and which to me is totally unpronounceable. So I'm not even going to call it anything except U1. Okay, so for this talk, it's U1. So what's special about it? Well, it was noticed as being special because of its orbit. The orbit is hyperbolic, so the eccentricity is bigger than 1. It's more open than a parabola. It's not bound to the solar system. And at first there was some doubt about that, but now there's no doubt about that at all. It's traveling too fast to be held back by the gravity of the sun. Okay, and in fact, it fell in towards the sun and is leaving now, will never come back, and we know that for sure. It's also highly inclined. It comes in a little more than perpendicular to the plane of the solar system, and it had a perihelion distance of about 1/4 of an AU, and the perihelion occurred before it was discovered. It was discovered on the way out, and we'll come back to that in a moment. So this little movie shows the trajectory of this thing falling in towards the sun. Here are the various planets, the sun in the middle, and it nips around perihelion, and then off it goes. It gets discovered as it passes the Earth. It came within 0.4 AUs of the Earth, and is leaving, and essentially is almost unobservable already, although it was only discovered just over a month ago. So this is the same kind of movie, but showing what you'd see following the object along. And also the planets are like individual comets. You can see their orbits trailing out behind. So here this thing comes. You have the idea it's really racing through. At perihelion, its speed was 200,000 miles per hour, which is totally staggering and unimaginable and so on. It's spending only 10 years inside the orbit of Neptune. So in 10 years, it crosses the solar system from Neptune's distance, which is 30 AUs, 30 times the Earth-Sun distance, all the way back out across Neptune's orbit distance in the other direction in just 10 years. So it's a very, very fast body. When it reaches infinity, it will still be traveling at 26 or 27 kilometers per second relative to the solar system. So it's a very, very fast body. So I got time on a couple of different telescopes. I have friends in Norway. It's an unusual thing for me to say, but I have friends in Norway, and I have other friends in Arizona. So I used a Norwegian telescope, no comment, a good one, very good one, called the NOT, the Nordic Optical Telescope, 2.5 meters, and 3.5 meter wind telescope on Kitt Peak to take pictures. These pictures are from the Norwegian telescope, and the telescope is tracked to follow the object, and the sausages are just trailed background stars. And I've removed them in this picture at the bottom. So it's a point source. It's actually observationally kind of dull. It's just a point source, like an asteroid, not like a fancy comet, which is what I was hoping to see. However, the brightness does change. So here are measurements from one of those telescopes as a function of time. And the brightness changes by a lot. So in this plot, here's 22nd mag, and it comes down to 23.5, but I have more data from the other telescope, and so in fact the range goes from about 21.7 down to almost 24. So it's a little bit over 2 magnitudes, so a factor of 6 or more in the light curve. And this is almost certainly due to shape. And so the physical reasoning is when you look at an elongated body side on, you see a big area and it scatters a lot of light. When it's end on, you see a small cross-section, it's relatively faint. And so as it rotates, you see the fat side, the thin side, the other fat side, and the other thin side. And so you have 2 bumps, 2 maxima per rotation, 2 minima per rotation. And the rotation is not perfectly determined. It's something like 8 hours. It's roughly a third of a day. Okay, so you've seen a representation of it like that. It's a giant flying sausage. The axis ratio has been described as 10 to 1. It's probably more like 6 to 1. There are various things that make it appear more elongated than it really is. It's roughly 400 meters long and maybe 60 meters effective radius. The mass is about 1 million tons, assuming a plausible density of ice or rock. It's about 1 million ton thing. And then this video you saw, so I'll just remind you that you've seen that and move on to save time. I measured the color of this thing. My expectation was it would be covered in this ultra-red material, which is something we see in the Kuiper Belt, but nowhere else in the solar system. And it's thought to be, by many people, to be irradiated organics. So you have carbon-bearing materials stuck on the surface of a body. Cosmic rays pelt that surface for billions of years, and they carbonize the surface, but also in some cases can make it go very red. I thought this thing would have the same ultra-red material on the surface. It does not. So here, these are 2 plots of, this is 2 axes of color. So more to the right is red, further up to the top is red. And these red dots are the red things I mentioned in the Kuiper Belt. Blue dots are other things in the inner solar system. They're labeled, Jupiter family comets, Centaurs, Damocloids, long period comets, the Trojans of Jupiter. This guy is just like the Trojans of Jupiter in its color. So in terms of color, it's not special. Here's the sun down here. It's a little bit redder than the sun. If you could see it by eye, it would be kind of a very, very marginally pink-looking thing, but nothing like a sweater or a bright color that you would see in this room. I also looked very carefully for atmosphere, for the evidence that there might be ice on the surface, because I expected there would be ice on the surface, because it's been out there in the interstellar medium probably for billions of years at a temperature that's probably like 10 degrees above absolute zero. And then this thing comes in close to the sun, gets warm, and you think the ice is going to begin to sublimate. There's no evidence for that. From the profile, I was able to set a limit on the mass loss rate that is, I think, stupidly small. It's 0.3 of a gram per second. Wow. Yeah, exactly. Thank you for the wow. That's really, really nothing. So if you had 1 square meter of ice on the surface of this body, it would sublimate more than that. So I know that there is not more than 1 square meter of ice on the surface of this object. Does that mean that it's an asteroid as opposed to a comet? People love that question. The answer is yeah, maybe, but not necessarily, because it turns out that you can easily shield ice buried in a body from the heat of the sun with a very small amount of refractory, non-volatile material on the surface. So if you had a layer of dirt only 0.5 meter thick, that thick, and the ice is down here, even the strong heat of the sun at perihelion, 1/4 of an AU away, the temperature is like 550 Kelvin. Even that intense heating wouldn't get down to the ice. So you wouldn't have any sublimation that we could see. And so it's either an asteroid, is rocky all the way through, or it's a comet with a dirt layer on top. And we know from many comets in the solar system that such dirt layers, they're called mantles, exist. Okay, so we can't really say comet or asteroid. I made this plot just to show why the thing was discovered when it was discovered. This is the day of the year. So 0 is January the 1st of this year. And 365, December the 31st is over there. Here's how bright it was, scaled from my own measurements taken last month. So it began the year at about magnitude 31, utterly unobservable, so faint. It came up, comes into the threshold of observability with big telescopes over there. But when it first became bright, it appeared very close in the sky to the sun. And big telescopes don't look anywhere near the sun because the sun is bright and frightening and it's hot and it's nasty. They look only in the nighttime, of course. Then it faded and came back and was discovered at point D exactly when it reached peak brightness by a survey telescope in Hawaii called Panstarrs. Okay, now here's the thing that freaked me out the most about this object. I tried to calculate how many of these must be in the solar system and how many there must be per unit volume in order to give a reasonable chance of seeing even one with this Panstarrs survey telescope in Hawaii. And the answer I get, and I've done it many times, and now other people have started to do it as well, and so I think it's correct. The answer I get is that there are 0.1 of these objects per cubic AU. Yeah? So 10 cubic AUs and you have one of these things. That means that in a cubic parsec, and a parsec is the average distance between the stars, there are 10 to the 15 of these. What's 10 to the 15 called? 1,000 trillion. It's got a name, but I forget what that name is. 10 to the 15, one followed by 15 zeros, a huge number. So if you work out the volume of space inside the orbit of Neptune and multiply it by that density of 0.1 per cubic AU, there are 10,000 objects with the size similar to U1 in the solar system now. And we only just saw the first one for the first time because our telescopes just are getting good enough to begin to see these things. So they've been whizzing through the solar system forever. We just picked up the first one of these objects. If they each spend 10 years in the solar system, that means that every year, 1,000 new ones come into the solar system and 1,000 others leave in steady state the solar system. That means 3 every day come into the solar system and 3 more on the other side leave. Pretty staggering. Where are they coming from? The interstellar medium. Where do they come from originally? They're ejected from the disks around young stars where planets are forming. So planetesimals in those disks that are not absorbed in the process of making planets can do a near miss, can be scattered by a planet and ejected from the system. So we think that our own solar system formed its Oort Cloud that way. We think that the Oort Cloud has roughly 10 to the 12 comets in it, but the 10 to the 12 are just the survivors of a much larger number, maybe 10 to the 14 comets that were ejected by our star. Most of them lost to the interstellar medium. Maybe only 1%, maximum 10% were captured into the Oort Cloud. And then once they're gone, they just drift among the stars and you never see them again. So this is an object formed in a disk around another star, some indeterminate place in the galaxy, some indeterminate amount of time ago. If you work out the total number of these objects in the Milky Way, it's even more staggering. So it's really good astronomy when you just can't believe anything that you calculate, but it actually is true. There are 10 to the 25 or 10 to the 26, so 25 zeros or 26 zeros in the Milky Way floating around between the stars. Awesome. Okay. So there are other interpretations. One of them, the first one, has appeared in a paper which you can read online in an archive service called AstroPH. And here it comes. You want to predict it? Here you go. Dark matter nugget. Ooh. So you know that there's this problem that most of the mass in the universe does not emit a measurable amount of light. So these people, the name is Cincinnates, maybe you pronounce that differently. Cincinnates and his colleague think that maybe this could be a nugget of dark matter coming through the solar system. and it's not emitting light, it's just reflecting sunlight, I guess, in their opinion. So maybe that's the case, but to be dark matter, it's got to be really dense. Imagine that it's as dense as a neutron. So a neutron or proton is about 10 to the 18 kilograms per cubic meter. The volume of this thing is 100 meters cubed, roughly, so it's a million. So a million times 10 to the 18 is 10 to the 24 kilograms. That's a big fraction of the mass of the Earth. So this little dot, 100 meters across, will be an Earth mass thing, according to these guys, flying through the solar system. And that is possible, except for two things. One, if you start shooting Earth mass things through the solar system, they disrupt the motions of the planets. And since there are 10,000 of them inside the orbit of Neptune, we would know. And second of all, an object that was that massive has enormous gravity and would pull itself into a sphere. It wouldn't be this elongated body. So we can reject that one. We also have the next one, which we've alluded to, an alien spaceship, which comes from my colleague Dave Page at UCLA. He had a conversation in my office. Dave, they're coming to kill us, I'm sure of it. And I said, Dave, that's not true. And you know it's not true because there are 10,000 in the solar system. What alien race is going to send 10,000 big spaceships to the solar system? And not one of them comes near the Earth. I mean, they're just incompetent if they're doing that. And then there's 10 to the 25 in the galaxy, so somehow I don't think so. But he thinks they're here to seed the Earth with bacteria. Okay, the kind of questions that are interesting, and I'm sure you have others. How long has it been out there? From where exactly did it originate? Where did it come from? When are we going to see the next one? Why does it have no surface ice? You know, when it's been so cold for so long, where is the ice? Why is it so elongated? And will the next ones look like the first one? Okay, so I'd like to open this up for questions.
Well, there are some questions. I'll start with, why is it so elongated?
Good question.
Thank you.
To which there is no known answer. So if you compare it, which is why it's a good question, if you compare it with the asteroids in the solar system, you see there's really an extreme shape. So the asteroids, if they're small in the solar system, often have axis ratios that are like, you know, the long one is 1.5 times the short one. They're kind of shaped like American footballs for the most part. So the long axis, 1.5 times the short one. Or if it's fairly extreme, maybe 2 times the length of the short axis. But this thing is 6 times or more, much more like a cigar or a pencil than it is than a peanut or something like that. So why would that be? Well, what determines the shape? It's a bunch of different things. In the solar system, collisions are important. So we know that collisions smash bodies and produce fragments, and this is a small enough object to be a fragment of a bigger thing. But we don't see fragments that are this elongated in the solar system. And so that may not be the explanation. If you spin something really fast, you can make it elongate because of its own centrifugal forces, but it's not spinning that fast. 8 hours is not that fast. You have to go much faster than that. So those explanations don't really work. Some people say, well, you know, maybe it's 2 objects. Maybe it's a binary. So you've got two round things like that stuck to each other. But that only gives you a factor of 2, because when you see them side by side, you've got pi r squared there and pi r squared there. And then when you see them end on, you've just got 1 pi r squared. So it's only a factor of 2. So that's no good either. So you have to have like 2 long things stuck end to end to make this extremely long thing, which just doesn't sound right somehow. So that's why I first thought it might actually be a spacecraft. When I first saw the light curve, I thought, seriously, could be. And only after I calculated there's 10,000 in the solar system to give any reasonable probability of seeing this one, did I kind of reject that idea.
What do you call a reasonable probability of detecting one?
Well, this was detected by the Panstarrs Sky Survey that has been operating at kind of peak efficiency, the current efficiency, for 1 or 2 years, something like that. So the observation is we have one object in surveying the sky for 1 or 2 years. And this object was only detected, I showed you that plot, was only detected because it came within 0.4 astronomical units from the Earth. So those are the conditions. Is one every 1 or 2 years, passing within a volume of 0.4 of an AU radius. Okay,
But if we just got lucky to see it within the 2 years, let's say the normal period is 20, then
Yeah.
your population density just went down by a factor of 10.
but do I look lucky? No.
No.
So
Well,
there's
odd
always,
things do happen. Odd things do happen.
yeah, I know. So it's a statistical argument,
Yeah.
and it's an argument based on statistics of one. So you can reasonably
Yeah.
question everything based on statistics
So yeah,
of
that's
one.
what, and I am. That's exactly what I'm doing. 'Cause
But I
anytime
think-
we make statements as confidently as you are about
Trust
the
me,
number when we have
trust me,
one.
trust me. Because one,
don't.
one is infinitely better than zero. That's my position.
Oh, it is, absolutely.
So we'll know. The point is, it doesn't matter what I think or you think. We'll know because we're going to detect more of these things because Panstarrs is not going to stop operating tomorrow. It's going to keep finding more. So my prediction is you'll find another one within a year, something like that, of this size, a small body like this. So we'll know. But the density comes from my assumption that it's been working properly for a year or two, and that the thing has to come closer than 0.4 AU to be bright enough to be detected. Yeah. Yes.
We had a kind of a question going on.
Yeah.
How do you know its shape as opposed to albedo, the
yeah.
reflectivity
Yeah.
that causes the light curve?
That's a good question as well. So when we look at bodies in the solar system, we rarely see large albedo variations over the surface. So the one notable exception is this big moon of Saturn, Iapetus. It's got a black side and a white side. There's a factor of 6, indeed, in albedo from one side to the other. But when you look at asteroids, you don't see that. And when you look at Kuiper Belt objects, you don't see that. And the reason is partly that the composition doesn't vary that much over the surfaces of these very, very small bodies. They're mostly just covered in dust. Micrometeorites are bombarding the surface, and the dust kind of flies away, but some falls back on the surface. So they're just coated in dirt, essentially. And in the case of U1, it's been bathed in cosmic rays, probably for billions of years, and isotropically. They come in from all directions, so there's no special place on there. There's no reason to think one place will be different from the other. And in addition, when you have a rotational light curve like this elongated pointer, which is about 4 to 1, when you have a rotational light curve, it tends to be nearly, but not exactly, symmetric. So you get a maximum and a minimum. Then the second maximum is a little bit different from the first one, and the second minimum is a little bit different from the second minimum because of slight differences between the two sides. But when you have an albedo feature, it just repeats. You just see the same bright spot coming back. So,
Okay.
yeah, it's an assumption, but I think it's a pretty solid assumption. Yeah.
Did we tag it with a sensor or something when it came close? And
I wish. I wish. We weren't caught unawares, but we were almost caught unawares. So this kind of thing has been predicted. Nobody really knew how many we'd expect to see, or the interval between seeing them. But this kind of thing has been expected for a long time. But there's simply no possibility of doing anything with it or with similar objects in space at the moment, because we don't have rockets that are ready, and even if we had rockets ready, they wouldn't be able to get there in time to meet this thing. It just came in, passed by, and disappeared so quickly.
just get it ready.
Well, you get them ready, but it still will be really, really a tall order to try to rendezvous with it. Yeah, I think in the distant future, like maybe 1,000 years from now, we'll be doing stuff like that.
It's just to say, come back.
So
in 500
hang around
years.
for that. Yeah. Yeah.
Yes, question.
When you track back from where it comes
Yeah.
from, did it come from Andromeda or the large giant
Yeah.
cloud? Or, is there a galaxy or something in the direction when you
Well, so it comes from our
we
galaxy.
shot the Voyagers at them, maybe they're shooting back at us.
It's retaliation. Yeah. There are many galaxies, right, in every direction you look.
Right.
But this comes from our galaxy, so it doesn't come from a distant galaxy. It comes from inside the Milky Way, somewhere. So the question really is, are there stars? Did it come from some nearby star? And people have already tried to do that calculation. But when you think about it, we've observed its position. We've measured its position for about a month. Yeah, and then the time it's going to take to get even to the nearest star is 25,000 years or something. So you're trying to extrapolate measurements from 1 month over 25,000 years, and you can't do that. And even if you could do that, that star wouldn't have been there, in 25,000 years. So it's kind of a hopeless problem. Most likely, it was not just deflected into us by a single star. Most likely, it gets a large number of small deflections. So it's bouncing around between many, 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 many stars. It never gets very close to any one of them, except, in this case, it came close to the sun. And so it's a whole series of small deflections. So it's like you're trying to play football, soccer, and instead of kicking the ball with a big kick, you give it a little kick, and so it goes in this direction. I'll be the ball now. So it goes in this direction. And then somebody else comes along, gives it a different kick in this direction, and then you keep getting these little random movements. With time, you move away from where you started, but very slowly. So it's basically diffusing through the galaxy like a molecule of smell diffusing through the air from the back of the room. No offense to anybody. Yeah.
Well, I'll go. I have two sort of observational questions. Did anybody get any kind of spectroscopy on it? And also, to identify others, will it always be based on a hyperbolic orbit?
Yeah, so there are some spectra. The first spectrum published was by a person who I know him very well. He used to be a grad student in Hawaii, where I used to work for a long time. And he's a great guy, but he published one of the worst spectra I've ever seen. So he was full of excitement. Everybody's full of excitement with this object. So everybody and his dog is out there with a telescope trying to look at this thing. So he was using Palomar, 5-meter telescope, on a really lousy night. And he took a lousy spectrum. And it shows that there is a spectrum. And that's about all.
One's better than none.
It's useful to know, yeah. But what you want to know is, are there any absorption features so you can diagnose what material is it made of? And it's so noisy you can't tell. But then if you can't get that, you'd like to know the slope. How red is it? And it's so bad you can't even get that. So there are a few others. We're still in the rumor stage, where it's rumored that this person over there might have a better spectrum. We'll see what comes out. But nothing good so far. The spectra basically are useless so far, although there are several of them. Will the next one be identified in the same way? Yeah, because the distinguishing characteristic is it is traveling faster than the escape speed from the solar system. And so it's not gravitationally bound to the solar system. It cannot be held back by the sun's gravity. And that basically is what we're looking for. So it's a hyperbolic orbit, but it's extremely hyperbolic and cannot have any origin in the solar system. Yeah.
Two questions.
Yeah.
One is
It's very hard to see against the light.
okay. One is your aggregate mass of all statistically of all of the objects in either the solar system or the galaxy, is that just infinitesimally small in terms of the total mass of either the solar system or the galaxy in terms of any gravitational effects that might be ascribed currently to dark matter?
Okay, that's a good one too. So if there are 10 to the 25 of these things in the Milky Way, each one has a mass of 1 million tons, which is 10 to the 9 kilograms. So 10 to the 25 times 10 to the 9 is 10 to the 34. I can just about add the numbers. And that's 10,000 times the mass of the sun. The sun is about 10 to the 30 kilograms. So there are something like 10,000 solar masses in these solid bodies, based on the statistics of one. Okay, I'll give you that. But, there are several times 10 to the 11 stars. So it's way down. It's way down in the noise, and it's not enough to be dark matter, unless this thing is made of neutrons or something. Yeah.
You've answered my question. The second question is, I saw someplace that it was coming in at speed x, and it was going out at speed x times 2. I forget what the exact number is. But it would seem to be coming in and going out at the same rate.
Yeah.
Decelerating.
I don't know where you saw that, but it's going to be symmetrical.
Okay, maybe it was time difference. Here's where you observed it, and it was coming in.
Yeah, maybe the
Here's
difference.
where you observed it.
Yeah, the difference between the speed at the instant of discovery and then in the infinite future or something.
Actually, Dave, may I ask, do we know its direction compared to the local standard of rest? Might it be getting a little gravitational boost from the sun?
Yeah, it came in roughly from the direction of travel of the sun.
Oh, did it? Okay.
did, yeah.
Then. Okay, don't you wish you could do that kind of math in your own head and answer these questions? I think that's pretty awesome. Last question here.
Are there any, I know this is kind of a far future thing, but would there be any implications for interstellar travel? Like, are there so many of these that it would be like trying to go through a hailstorm?
No. Let's think about that. So I just do the calculation. If there's 10 to the 25, each one is, say, 100 meters across. So the area of each one is about 10 to the 4. 10 to the 25 times 10 to the 4 is 10 to the 29. And then say the galaxy is kind of a disk with a radius of 10,000 parsecs is about 10 to the 20. So square of that is about 10 to the 40.
Okay.
So it's 10 to the 19 compared, was it 10 to the 19 compared to 10 to the 40? So it's negligible. It's like 10 to the minus 20 or something. Yeah.
Okay.
So what that means is, and it's the same with stars actually. We have 10 to the 11 stars, and they're big, but the spaces between the stars are so big. If you got a stick, if you had a galaxy like that, the Milky Way is this big flat, 2 fried eggs back to back like that, and you get your stick and you start plunging the stick through, you would only hit a star one every 10 to the 12 times or something. And you'd only hit one of these guys every 10 to the 21 times. So you have to do a lot of that before you get one. And why would you do that?
I would have to sell my ticket then.
Yeah.
So once again, I have to say, isn't it fun to be able to do math like that? And when you are a student, one of the first things you learn is how to do these kinds of order of magnitude estimates, because these kinds of general questions you have, ooh, isn't that great to be able to just get an answer? So with that, I would like to thank you again, Dave, for coming and telling us about this extraordinary object from
You're
another
welcome.
solar system.
Thank you.